Hello friends, in this video we are going to study about linear variable differential transformer, which is also known as LVDT. In this video we will study the construction, working and some of the applications and advantages and disadvantages of LVDT. So let us start with our topic. The linear variable differential transformer, which is also known as LVDT, it is a most widely used inductive transducer. So here transducer, they are those devices which convert the non-electrical quantity into an electrical quantity, and inductive transducers means that they are by some means they are changing the inductance of the coil, and due to the change in the inductance the non-electrical quantity is converted into an electrical quantity. So here this LVDT, it is used to measure the displacement, and this displacement is measured by measuring the output voltage. So here displacement is changed into an electrical quantity, which is the output voltage. Okay, so we are measuring the displacement, which is a non-electrical quantity, and this displacement is measured by changing the inductance of the coil. Okay, inductance which is linked with the coil, and this displacement will be measured with the help of the output voltage. Now here it is named as the linear variable differential transformer. It is called a transformer because in this LVDT we will have two types of windings, primary winding and secondary winding, just like the windings present in a transformer. So here also we are having the two types of windings, primary and secondary. That is why it is called a transformer. Differential transformer because the output of the transformer, it is the difference between the voltages across the secondary windings. So the output voltage, it is the difference of the voltage, that is why it is called differential transformer. And linear variable because it is measuring the linear displacement. So linear motion is converted into a voltage. Okay. So this linear variable differential transformer, we have described the meaning of every word in this LVDT. Okay, linear because it is translating the linear motion into electrical signals. Differential because the output voltage, it is the difference of the voltages. And transformer because it is having two types of windings, primary winding and secondary winding. Now let us first see the construction of this LVDT. Let us see what are the various parts of LVDT. So this is the basic construction of the LVDT. In this diagram, you can see that we are having the two secondary windings S1 and S2 and one primary winding P, which is being wounded across a cylindrical former. Now in between these windings, we are having a soft iron core, and this iron core is moved between the windings. Okay, so displacement is being given to this soft iron core, and the output voltage, it is measured between the two secondary windings. The input voltage, it is being applied to the primary winding, means primary winding is excited by an alternating voltage, and when this voltage is applied to the primary winding, a magnetic field will be generated, and when this displacement is given to the soft iron core, so the flux linked with each of these windings also changing. So according to that, the output voltage from these two windings, that also changes, and by measuring the output voltage, we can measure the displacement in the soft iron core. So if we talk about its construction, we see here that we are having single primary winding, which is denoted by P, two secondary windings, S1 and S2. Now these windings, they are wound on a cylindrical former. Now these two secondary windings S1 and S2, they are having equal number of turns. So these two secondary windings, they are having equal number of turns, and they are identically placed on either side of the primary winding. Means at an equal distance, they are placed on both the sides of the primary winding. Now, if we talk about the primary winding, this primary winding is connected to an alternating current source. Now, the soft iron core, so this was the main components present in the LVDT, or we can say this is the basic construction of the LVDT, having one primary winding, two secondary windings, and one soft iron core. Now this soft iron core, you can see that it is placed inside the former. It is in the middle of this former, and to the soft iron core, a arm is attached, and the displacement which we want to measure, it is being given to this arm. Okay, through this arm, this soft iron core is moved inside the former. Now if we talk about the material through which of which this soft iron core is made up of. Now this soft iron core, it is made up of high permeability nickel iron, and this soft iron core is hydrogen annealed. Now why this is being done? Because when it is hydrogen annealed, this gives low harmonics, low null voltage, and high sensitivity to the LVDT. Also, this soft iron core, it is slotted longitudinally so as to reduce the eddy current. Okay, now this whole assembly of this LVDT, it is placed in a stainless steel housing, okay, so as to protect it from the environmental conditions. Now, this complete assembly of the LVDT, it is placed in the stainless steel housing, and the end lids, they are going to provide the electrostatic and electromagnetic shielding, so that if any stray magnetic and electric fields are present, they cannot disturb the working of the LVDT. Now here we have seen that the primary winding, it is excited by an alternating current source. So the frequency of this AC applied to the primary winding, it is between 50 hertz to 20 kilohertz. Okay. So this was the complete construction of the LVDT. Now let us see the working, that how this LVDT works and how the output voltage generated across the secondary windings, that is used to measure the displacement. Okay. So now we will study the working. Now, as I have said that the primary winding, it is excited by an alternating current source, and the frequency of this current source is between 50 hertz to 20 kilohertz. So due to this alternating current flowing through this primary winding, or the excitation of the primary winding, electromagnetic field is being produced. Okay. So this induced electromagnetic field, it is going to induce the alternating currents in the two secondary windings. So the when the primary winding, it is excited by an alternating current source, it is going to generate, or it is going to produce an electromagnetic field, and that electromagnetic field is going to induce the alternating currents in the two secondary windings, S1 and the S2. Now let us suppose that the alternating current voltage, which is induced in the two secondary windings, for the secondary winding S1, suppose the voltage is ES1, and for the secondary winding second S2, the voltage is ES2. Okay. Now, in order that the two, we are getting a single voltage from the output of the LVDT, what we do, we connect these two windings in series opposition. Okay, so when the voltages, they are induced in these two windings, secondary windings, so from this we are getting ES1, and from second we are getting ES2. Now from LVDT we want only a single output voltage, so what we will do, we will connect these two windings in the series opposition, so that the output voltage which we are getting from the LVDT, it is the difference of the voltages in these two windings, that is E naught, which is the output voltage, it will be ES1 minus ES2. So that is why we are getting a differential output voltage from the LVDT. So the output voltage which we are getting from the LVDT, it is the difference of the voltages in the two windings. So E naught will be equals to ES1 minus ES2. Now when the core, when the soft iron core, it is at the null position. Now when this soft iron core, it is at the null position, means it is exactly at the middle position, then the flux which is linked with these two windings, these two secondary windings, that will be equal in magnitude. Okay, so equal voltages will be induced in these two secondary windings. So when we will get the output voltage, it will be 0, because ES1 is equals to ES2 at the null position. Now when this soft iron core, it is moved to the left position, then the flux linked with the secondary winding S1 will be more as compared to S2. So output voltage means this ES1, it will be greater than ES2. Okay, so the output voltage will be ES1 minus ES2. Now if this soft iron core, it is moved to the right hand side. Okay, so towards the right hand side, the flux linked with the secondary winding S2 will be greater than, so ES2 will be more than ES1. So the output voltage will be ES2 minus ES1. Okay, so in this way, the displacement which we are doing in this soft iron core, it is changing the magnitude of the output voltage. When the soft iron core, it is exactly in the middle, means it is at the null position, then the output voltage is 0. If it is more towards the left hand side, then ES1 minus ES2, and when it is more towards the right hand side, then ES2 minus ES1 will be the output voltage. And also in this case, when the core is moved to the left of the null position, the output voltage, it is in phase with the input voltage. Okay, now when core is moved to the right of the null position, ES2 will be greater than ES1. So output voltage will be ES2 minus ES1. And in this case, the output voltage is 180 degree out of phase with the primary voltage. So here you have seen that according to the displacement given to the soft iron core, the magnitude of the output voltage is changing. So here we can conclude that the amount of voltage change So the amount of voltage change in either of the secondary winding is proportional to the amount of movement of the core. Okay, so whatever by which displacement we are moving the core, that displacement will be equal to the amount of the voltage change in either of the secondary winding. Also, if we are doing this measurement, we are saying that whether this output voltage is in phase with the primary voltage, or whether it is out of phase, 180-degree out of phase. Through that also we can see the direction of movement of the soft iron core. So by measuring the amount of voltage change in either secondary winding, it is proportional to the amount of movement of the core. So this is going to give us an indication about the linear motion of the soft iron core, that in which direction the soft iron core is moving. Because whenever we are moving the soft iron core, the voltage linked with the two secondary windings, it is changing. Either it is increasing in one of the winding and decreasing in the other winding. So by checking the magnitude and the phase relationship of the output voltage, we can get an indication of the linear motion, or we can say that we can measure the displacement of the soft iron core. Because we have seen that when the soft iron core, it is at the null position, then we are getting the output voltage as 0. When we are moving the soft iron core to the left side, the output voltage we are getting is positive, and also because ES1 is greater than ES2 in that case, and we are getting the output voltage as the difference of these two, so we are getting a positive value. And also the output voltage, it is in phase with the source voltage, okay, or the primary voltage. So by checking the magnitude and phase relationship, we will get to know that the soft iron core, it is moved to the left side. Now when the soft iron core is moved to the right hand side, then ES2 is greater than ES1. In that case, the output voltage, which is the difference of these two, ES2 is greater, so we will get a negative value. And also the output is 180-degree out of phase with the source voltage. So again, by checking the magnitude and the phase relationship, we will get to know that the soft iron core is moved to the right side of the null position. So in this way, both the direction of the movement of the soft iron core and the amount by which it is moved, because this amount of voltage is proportional to the amount of movement of core. So the magnitude of output voltage is proportional to the magnitude of the displacement. So in this way, the LVDT, it can be used for the measurement of the displacement. It is converting the movement of the core or displacement into an output voltage. That is why it is called a transducer, because displacement is a non-electrical quantity and voltage is an electrical quantity. So non-electrical quantity has been converted into an electrical quantity. So the amount of output voltage, it may be measured to determine the displacement, and also this amount of output voltage will be proportional to the displacement, okay, they will be linearly related with each other. Also this output signals may be applied to a recorder or to a controller, so that it can restore the moving system to its normal position, okay. So that again, after the measurement, the soft iron core, it comes to its null position. Now, as I have said that this amount of output voltage, it is used to measure the displacement. So, how this output voltage, I have said that it is proportional to the displacement. So, they are linearly related with each other. But for some value of measurements, like for say up to 0.5 mm of the displacement measurement, there will be a linear relationship between the output voltage and the displacement. So let's see the variation of this output voltage with respect to the displacement, that how this displacement varies. So when the output voltage of the LVDT, it is a linear function of the core displacement only for a limited range of the motion of the core, and say it is about 5 mm from the null position. Okay, so when the core it is at null position, and when it is moved to 5 mm in the left hand side and to 5 mm in the right hand side, the output voltage will be proportional to this displacement. After that, there will be a non-linear relationship between the output voltage and the displacement. Let's see the graph for it. Now when the soft iron core, it is exactly at the middle position, means at the null position, so at that time the output voltage is 0. Okay, this is the null position here, and output voltage is indicated here, so output voltage is 0 at this position. Now when this soft iron core it is moved to the left hand side, suppose at a position A. Okay, so at this position A, the output voltage that will be greater than, means ES1 is greater than ES2, and we will get a positive value for the output voltage. And also the phase angle, it will be, means it is in phase with the primary voltage. Suppose the phase angle is 60 degree. Okay, so less than 90 we will get the value of the phase angle. And when this soft iron core it is moved to the right hand side, okay, suppose at a position B, so at that time ES2 will be greater than ES1. We will get a negative value for the output voltage, and also the output voltage is 180 degree out of phase. Now this range A to B, this range will be from 0 to A, or we can say that from 0 to B, these are approximately 5 mm of the null position. That is, in the 5 mm of range, we will get a linear relationship between the output voltage and the displacement. After that, you can see that the relationship is a non-linear relationship. Okay, and also the phase is also changing. Here we are getting an out of phase signal, and here we are getting an in phase signal. Okay, now also at this 0 position, you can see that some of the voltage is present, which is called the residual voltage. So ideally at this 0 position, means at the null position, the output voltage should be 0. But there is some small amount of voltage which is present, that is called the residual voltage. Now what are the reasons, or what are the factors due to which this residual voltage appears? So this residual voltage, ideally at the null position, the output voltage should be 0, but there is a small amount of voltage which is present at the null position called the residual voltage, and this residual voltage can be present due to the presence of harmonics in the input supply voltage, due to the harmonics produced in the output voltage on account of the use of the iron core, because we are using a soft iron core. So due to that soft iron core, in the output voltage harmonics can be produced. Also there can be an incomplete magnetic or electrical unbalance, or both can be present, and due to that unbalance the harmonics or the residual voltage is being produced. Now the magnitude of this residual voltage, it is less than 1% of the maximum output. However, this residual voltage, it can be reduced by using an improved technological methods, and also with the use of the better alternating current sources, so that the harmonics cannot be produced, and this residual voltage can be reduced to a negligible value. So due to the environmental conditions, or due to the stray magnetic and the electric fields, or due to the defaults in the AC sources, this residual voltage is being produced, but it can be reduced, it is produced, but it can be reduced to some negligible values also. So this was all about the construction and the working of the LVDT, that how the LVDT is measuring the displacement by measuring the output voltage. Okay, now let us see some of the advantages of the LVDT. The first and the foremost advantage of the LVDT is the high range. High range means that the displacement which we are measuring from the LVDT, it provides a very high range of displacement to be measured. This range of displacement measurement is 1.25 mm to 250 mm. Okay, so this high range of displacement, it is providing a very good range to be measured from the LVDT, and also with a 0.25% full scale linearity. This LVDT, it can measure the displacements up to a lower range of 0.003 mm, means that such minute displacements can also be measured with the help of the LVDT. So you can see that it is giving us a very high sensitivity, and the range of displacement that can be measured, that is also very good. But the dynamic response of LVDT is very slow. Okay, now second advantage of LVDT is the friction and electrical isolation. Now as the LVDT, it is a type of transformer, so it is having both the primary and the secondary windings, and also a soft iron core is also present. So here you can see that the core and the coils, that is the primary and the secondary coils, they are very means they are not close to each other, they are far apart. Okay, coils are present separately, and soft iron core is also present separately. Also there are no moving parts, no physical contact is there between these, the coils and the core, the iron core. So due to that, no friction is produced, and also there is an electrical isolation between the core and the coils of the LVDT. So due to that, no wear and tear is being caused, no friction is being produced, no damage of the parts of the instruments are there. So the life of, or the operating life of the instrument is being increased. So there is no physical contact between the core and the coil, so there is no wear and tear. So as no friction is produced, and also friction and electrical isolation is there between the core and the coils of the LVDT. So this gives the LVDT a very infinite resolution property throughout its operating life. Means very minute changes in the displacement, they can be accurately measured by the LVDT. Next advantage is immunity from. So as the core and the coils of the LVDT, they are separated from each other. So any environmental factors like corrosion or due to the shock or any corrosive fluids are there which can damage the parts, their effects will be reduced. Okay. So environmental conditions like pressure, temperature, they cannot affect, or any shocks or vibrations, they will have less effects on the parts of the LVDT. Okay. So that is the third advantage of the LVDT, that it is having an immunity from the external effect. Because also we have seen that the complete assembly of the LVDT, it is placed in a stainless steel body. Okay, so it is also sealed from the environmental factors, so that they cannot have any influence over the working of the LVDT. Next advantage is high input and high sensitivity. The output of the LVDT is very high. There is no need of any amplification. Means LVDT does not require any amplifier. It gives a very high amount of output also. And this high sensitivity means that the LVDT, it is sensitive to very minute changes in the displacement. We have seen that it can measure the displacement of very low values like 0.003 mm of displacement can also be measured. So it gives the LVDT a very high sensitivity, and high input or high output is produced from it. Next advantage is rigidness. Now the transducers means the LVDT, it can work in very stressful environments also. Okay, so it can tolerate a high degree of shock and vibrations because it is being sealed in an assembly. Okay, so this provides the LVDT a very high rigidness that it can tolerate the shock and vibrations. Next is low hysteresis. Hysteresis is the effect that when we are increasing the input values, and we are getting an output. Okay. Now, when we are decreasing the input, we are not getting the same output values. So that is an hysteresis effect. And in the LVDT, it is having the low hysteresis effect. So that is an advantage of LVDT. And due to this low hysteresis, it has a good repeatability. Also, another advantage is low power consumption. The LVDT, it consumes very less power. Also, its size is very less, so it can be moved from one place to another. Okay, so another advantage is the low power consumption. So these are some of the advantages of the LVDT. Now let's come to the disadvantages of LVDT. The disadvantages of LVDT are that the if we are measuring a very large displacements, then we have to produce a very large differential voltage will be produced. So it is difficult to measure a large amount of displacement through the LVDT. Also, we have said that because we are having a shield over it, we have kept the assembly in a stainless steel body, but also some stray and magnetic and electric fields, they can influence its working, but in that case shielding can be provided. Okay, but this comes in a disadvantage of the LVDT, that it is very sensitive to the stray magnetic and electric field. So the performance of this LVDT, it is also affected by vibrations, temperature, or can also affect its performance. And also the dynamic response of LVDT is very slow. So these are some of the disadvantages of LVDT. Now let us see some of the applications and uses of LVDT, that in what fields we can use the linear variable differential transform. Now, as the LVDT, it is measuring the displacement, so it can be used in a wide variety of applications wherever we want to measure the displacement. And it is acting as a transducer, so the displacement is converted into the electrical signals, voltage it is converted. So it can be used as a primary transducer also and as a secondary transducer also. Primary transducer, because we have seen that it is directly converting a non-electrical quantity into an electrical quantity. Displacement is converted into voltage. So it can be used as a primary transducer wherever we have to measure the displacement or convert it into the electrical signals. Now, if we see its use as a secondary transducer, it can also be used for the measurement of force, level, pressure. Like we can use the LVDT with the Bourdon tube. Okay, so Bourdon tube, in the Bourdon tube we will apply the pressure. Due to the pressure, the displacement will be caused in the Bourdon tube, and this displacement will affect the displacement of the iron core in the LVDT, and due to that the voltage will be produced. So what we are doing, we are measuring the pressure changes by measuring the output voltage. So LVDT can also be used for the measurement of force, pressure, weight by using it as a secondary transducer. The primary transducer can be Bourdon tube, it can be load cells, it can be strain gauge. Okay, they can act as the primary transducer, and LVDT will act as the secondary transducer for the measurement of these these physical quantities. For measurement of displacement, the LVDT, it will act as the primary transducer. So these are the uses of LVDT, that it can be used in the applications for the measurement of the physical parameters, displacement, force, torque, pressure, level. For these it can be used as both primary and secondary transducers. So in this video, we studied about the inductive transducer, linear variable differential transformer, which is also known as LVDT. First, we studied its construction, then we saw its working, and then its advantages, disadvantages, and in the last, we studied its application. So I hope that this topic is now clear to you. Thank you.